I'm at the Duke Quantum Center at Duke University. Duke Quantum Center is downtown, not on the beautiful campus you see here. And I just need to disclose that I have a financial interest in the quantum computing company. Thank you. All right, so 2025 is the International Year of Quantum Science and Technology. And I thought this tagline, which 100 years of quantum is just the beginning, is like a fun tagline. And it made me think about what else do I know that is 100 years old? And the thing that came to mind was my grandfather. So my grandfather is currently 102 years old. And it's kind of amazing to think about in that he's basically born before the Schrodinger equation. And then I think it's neat to kind of think about the technological progress that's happened because of quantum mechanics and the Schrodinger equation. So in 1935, people could start to apply it through chemistry, through things like Hartree-Fock calculations. Early NMR got started. Um, of course, in the 1940s, there was also atomic energy and atomic weapons. In 1947, it led to things like transistors and atomic clocks. And then finally lasers. And then 1976 is interesting to me because kind of at the halfway point is the first part where we have a technology which actually relies on coherence between multiple quantum particles. I think Shor's algorithm in 1994, which to me really kicked off the whatever technical got people really working on building quantum computers, even though it was, there were early ideas in the 80s, said actually, if you could have thousands of coherent things acting together, you could actually do computational problems that are quite challenging. And then very quickly after that, the first demonstration of the Shor algorithm was done on NMR by Hertz Fellow Dr, who also wrote a very nice textbook at that time on how to do quantum computing and who I did my postdoc with. The reason it could happen with NMR in 2001 was because people already had pretty advanced NMR systems because they'd been doing two-dimensional NMR since 1976. Okay, so what is a quantum computer? I think it's just useful to think of it as a different kind of processing unit. And you just want to think about it as something which will accelerate. There will always be a classical computer which is talking to the quantum processor. So you could think of it like, say, a GPU. Um, so in 2019, the National Academies put out this really great report, and I'd still recommend reading it. It basically looks at like what it takes to build a quantum computer. And one thing I just wanted to focus on here is that you see in this bottom corner, that's the part of the superconducting quantum computer, which is some sense quantum. That's like the quantum fabric. Everything else is still a lot of classical engineering, classical RF engineering, classical electronics, and that is going to remain true. So I think in terms of the way that scientists and engineers can contribute to quantum computing is quite broad. It doesn't necessarily rely like getting all the way to the bottom quantum piece. So what does this QPU accelerate? So Peter Shor again showed that accelerated factoring, which breaks all kinds of public key cryptography. For those of you who watch the old movie Sneakers, it's basically the machine in Sneakers. It's also really good for quantum simulation because it allows us to directly represent wave functions with wave functions. It's good with problems with symmetries. It's good for optimization. There's all kinds of unstructured search. And there's actually a nice website that has a whole bunch of algorithms that you can do things with a quantum computer. Of course, everybody wants to know, how does it work? Well, my simple analogy is at the end of the day, a classical computer is a thing which takes a number, and we can have all numbers be bit strings. So there's a bit string A, and it just maps one bit string to another bit string. This whole Zoom conversation is exactly that. My computer turns me into bit strings, sends those bit strings over the internet. Your computer projects me onto your screen. Now, what's cool about classical computers is we, of course, can copy things. We can even copy whole computers and pause them. And that's how it works. So a quantum computer, the basic thing is that because of quantum mechanics, this kind of wave particle duality, I like to think of it as basically, instead of having, if you think of a bit string as a particle of information, we now actually have waves of information. So we can have a wave function psi, which is a superposition of two classical bit strings. These coefficients here are complex numbers. We can apply operations that rotate the state. So we can rotate this state to a classical bit string and back and forth. And then the weird thing is when we do the readout. So when we do readout, we collapse to either A or B with probabilities that are the square of these probability amplitudes. This is actually, so it's very fascinating because we can make like this wave of information that has all these superposition of many bit strings. But when I ask the quantum computer what's going on, it just gives me one bit string. This also basically is one of the reasons what makes it impossible to copy. So in the middle of the quantum computer, if we wanted to like map a copy of the state to save it for later, to, just back up things on a quantum cloud, you can't do it. You have to actually process through the whole information. You can't copy it on the way as it goes. So if you'd like to learn more, and depending on your level, of course, so we had an expedition in computing group that was funded by the National Science Foundation. This is Peter Shore again, and this is Diana Franklin. Diana Franklin's an expert in computer science education. And we actually built a whole bunch of materials from like K to 12 to teenagers to experts to try to help people understand. So I think this is a great resource that points to a lot of other excellent resources to get more information. So the interesting thing with quantum computers is that any quantum system could be the quantum computer. And I like to think about it with respect to, say, the classical computers, say vacuum tubes and transistors. So vacuum tube computers were like super useful in World War II. And actually, transistor was invented in, say, 1945. But companies like IBM were still selling vacuum tube computers into the mid-50s because it took time for the transistor to turn into the modern computers we have now. So at present, these are just a few things. Like the early ones, again, used NMR because NMR machines were just very good, very capable. There's a lot of work with photons, neutral atoms, electrons floating on liquid neon or helium, electrons trapped inside of quantum dots, atomic ions, which float above these electrode surfaces, superconducting qubits, where basically at this Josephson junction, you allow these things to happen. And there are a lot of choices. And I would say all of these, except perhaps NMR, are really actively being pursued still. And many of them have startup companies and even like large companies invested in them. So I like to split it roughly into two types. So on the left, I think of these like natural qubits. And so I think about atoms and ions and photons. So what's really nice about them is that every qubit's the same by nature. I can buy calcium ions here, calcium ions in Europe. They'll have the same frequency, everything's the same. They have a weak coupling to the environment, which is good for having long coherence times. And then the challenge is like in the control and confinement. So like, for example, in this paper, working with collaborators at Lincoln Labs in Berkeley, we basically said, well, what if we had like an amazing trap? If we had the amazing ability to fabricate this trap, which again, everything here is just basically classical, and it's just to interface with this atomic ion, which would float above the trap. On the other side, I like to think of sort of synthetic qubits. Every qubit's the same up to manufacturing defects. Because they're not, because they're often in the solid state, they're stronger coupling to the environment, which makes the challenge of like charge noise, flux noise, all these things hard. And the synthetic qubits will always say, well, we can print as many as you want to fit on a chip. And here's an example where really nice work from HRL, where they printed 6 different dots, which they used to make 2 qubits. But I do think this difference is really true. So this is some really interesting work on the left from last year from Harvard, Cura, MIT, UMD, NIST collaboration, where they looked at doing Rydberg quantum computing. And there's a part where they want to do 2 qubit gates in parallel. And what's amazing is they can just send one control laser. That one control laser turns all these 2 qubit gates on at the same time because every atom, in this case, rubidium atom, is exactly the same. So you don't like if you want them all to do the same thing at once, the control is very easy. And then on the right, I think again, in these synthetic qubits, you're limited by our ability to fabricate, but of course human beings are super good at fabricating things and super good at like making the errors lower. So in this plot here, so they make these larger arrays of superconducting qubit arrays. The red blocks here are what their normal process would do in terms of having a width in their desired frequency. Like if fabrication was perfect, every one of these would have exactly the same frequency. But because it's not perfect, you get this spread. But then what they can do in this paper is they go through with a laser and they actually re-anneal them. And they do it in a way where you now have two different frequency sets, which are much tighter. And so that's great, right? That's the sort of progress we expect on both sides. So I'm just going to talk a little bit about why I think there's still a lot of space to think about hardware. So we think about qubit design, transmon qubit, which is the qubit used by Google and IBM and many others, was designed in 2007. It's basically an LC circuit where this inductor here is nonlinear due to these two Josephson junctions, so kind of like a squid loop. What's amazing, in 2010, there's a Nature paper highlighting different ways to make quantum computing hardware. The first author, Thaddeus Ladd, is actually a Hertz Fellow. He was a Hertz Fellow when I started. He started at Stanford when I was at Berkeley. What's amazing is this paper is after this discovery, and the transmon, which is the dominant kind of dominant superconducting qubit now, wasn't even highlighted. So in the picture of ways to make superconducting qubits, it just didn't make the cut. And it's because at this time, it hadn't yet caught up with these already existing superconducting qubits. By the time you get to 2019, everything's basically a transmon. And in this really nice tutorial on engineering of superconducting qubits from Will Oliver, who's at MIT and works with Beatrice, they basically, all these things there's like transmons, and then people want to use a different name, but they're effectively transmon-like. And it's because they have good sensitivity to noise, and you get these nice kind of flat regions. That pushed ahead the industry. So here's like the first Google experiment with, they had these nine transmon-like qubits, this IBM quantum experience, which led to this IBM cloud of allowing tons of people to interact with them. And you'll notice that you can actually, see the circuit, see the way the metal is put on the surface. Both companies have like expanded to many, many qubits, printed more and more qubits. These are not their most recent devices, but just some example devices. And what you see is, again, like they achieve this goal of scaling ups. But you also will, if you look at the papers, see that there's like no more details. Like you no longer could look at the paper and think about how to fabricate these things. Now, synthetic qubits are great because they really are a choice. And if even in the context of just superconducting qubits, you could pick different levels of Josephson junctions and inductors and put them together in different ways. And one kind of cool thing is to say, oh, actually, what if I try to use the strong coherence of the microwave cavities to improve the coherence of my qubits by actually putting the information into the photons that are in the microwave cavity. And this is an idea called superconducting bosonic qubits. They allow you to make kind of cool states called GKP states. And there's actually a bunch of startup companies that are using this as their direction for their future quantum computers. Now, as I mentioned, atomic qubits are the same, but basically no real physical system, very few physical systems are just two-level systems. So when you turn it into a qubit, you've made some choice. So this is an example of kind of a typical ion level structure. We usually work with, on purpose, ions that have a single electron in the valence shell. And so the ground state is usually an S-type electron. And then you can excite up to these p states, d states, and you actually have qubits here in the ground state, which are between the spin or hyperfine. You can have a qubit between the ground state and this quadrupole kind of metastable state, which forms an optical qubit. You could have a qubit just in the metastable state. And there's a nice work from from Oregon and NIST and UCLA, basically saying, look, there's all kinds of things you can do, and you can actually use these different qubits at different parts of the experiment without changing your hardware. Uh, I thought a little bit about how you can use it to control the error, and that work was really inspired by some nice work on neutral atom erasure, led by Jeff Thompson, who's actually was also a Hertz Fellow and is now a professor at Princeton. So, focusing a little bit on ions. So we use Raman lasers to do the gates. We've used a lot of 171 ytterbium ion. It has the property that um, basically, from a lucky, it's just luck. It is really just luck. So a 355 nanometer laser, which is relatively cheap, it's used to cut masks to make regular computer chips. Turns out to have a really nice detuning between these two excited electronic states. And so by driving this stimulated Raman transition, we're able to control this 2-qubit gate. We have really low errors in terms of single qubit gates. These are our 2-qubit errors in our lab. The coherence for us is usually around a second, while the gate times are microseconds. But work in China has had a gate time up to an hour. So it's really quite robust because this hyperfine state here is insensitive to magnetic fields. Now you want to put them together into a computer. We've been looking at these ion chains. We use these surface electrode traps that are built at Sandia National Labs. The ions float above the surface here. Individual beams allow us to control the ions on and off, and the global beam allows us to kick to create this motion. And there are many projects, ARPA projects, NSF projects, DOE projects, which use this basic setup. I do think there's a lot of work going forward thinking about ion trap fabrication. So ion traps initially are just like a 4-rod quadrupole trap. And in 2005, John Chinorini at NIST basically realized you could kind of unfold a 4-rod quadrupole trap onto a plane. And that allows you to take advantage of 2D fabrication. It allows you to actually put the electronics directly beneath the chip, which was first done at Georgia Tech Research Institute when I was at Georgia Tech. And then GTRI collaborated with Honeywell, which actually eventually led to Honeywell spinning off a quantum computing company called Quantinuum. Yeah, so this is again a picture of the Sandia trap we use. But it'd be really nice when we think about scaling up, how can we actually integrate lasers, which is our control wires to control these different ions? And that's a current challenge that everyone is working on. And this is some nice work from Lincoln Labs, actually showing that they control and trap a single atomic ion. Okay, so I wanted to talk about this 2019, just get back to this 2019 report. So in that 2019 report, this is like where the world was. This was the roadmap of what we should do in time. I'm not going to talk about the annealing time. There's been good progress in the annealers as well, but I'm just going to focus on the right. So what's amazing is the first thing is this quantum supremacy. What does quantum supremacy mean? What it means in this case is that the quantum circuit generates a distribution of classical outcomes that is hard for a classical computer to fake. So it's kind of like we've built a race, which the quantum computer is really good at. We've like focused on that. And then of course it can beat the classical computer, but it has to have like a number of qubits. So that's been done in both superconducting qubits, multiple groups, and now done ions with this Quantinuum company. Quantum error correction, which I will talk about at the end a bit. That basically, so working with my collaborator Chris Monroe, who was at Maryland at the time, we were able to show kind of like a small quantum error corrected circuit. But what's been nice is in the really recent papers by Quantinuum and Google, they've done this repeated measurement of error correction and shown some actual improvement for multiple systems. And what's nice is this Google one, in some sense, satisfies both this idea of having a gate-based quantum computer with hundreds of qubits, which was done already earlier by, say, IBM, and now with these Harvard Rydberg atoms, but also is a gate-based quantum computer with hundreds of qubits running QEC. This one is something everybody's still trying to hit, which is can we find something useful to do with a quantum computer without going full-blown quantum error correction? And this depending on who you talk to, people would say we've already done it or not. So in this particular example, which is from Quantinuum, they use this random distribution that you can only get from a quantum computer quickly to verify the server you're talking to is actually generating random numbers. So the server has to send you these random numbers quickly. You actually have to have a supercomputer which models like what you expect these things to be. And then you can show that if this can do it relatively quickly to your ability to run it on like, Frontier at Oak Ridge, you can say, okay, with high probability, these people must have a quantum computer and it's doing these random circuits well. And so there are a lot of some cryptographic protocols where if I can actually guarantee randomness with the server, there's a huge gain. All right, so what's stopping us? So right now, there are not that many qubits. There are hundreds of qubits, and the error is, say, maybe 10 to the minus 3. There are different things you'd like to do. Maybe you want to steal Bitcoin. Maybe you want to simulate molecules. Maybe you want to do physics models. And the problem is these things are they're pretty far out there. So so if I wanted to do a chemistry algorithm, like try to understand nitrogen fixation, the original estimates is you need kind of like an operation error of 10 to the minus 15. And there have been a lot of improvements. And, I'm part of an institute for robust quantum simulation, which continues to try to fix these things. So how do you get there? Well, you can make the controls of your quantum computer better and better and better. But the cost of that is like people have different arguments about how far this will go. There's some really interesting microwave ion trap gates where it's hard to write down what the fundamental limit is. But I'd be quite happy if we could get to 10 to the minus 6, and that still leaves a pretty big gap. We can improve the problem. This is actually pretty cool because sometimes you actually improve the problem too much and then it becomes easy to do on a classical computer, which is a win for humanity, but bad for quantum computing. You can scale the hardware up and then you use quantum error correction to basically get back to solving this problem. But this is like a huge cost in scaling to bring back this thing. But for example, this factoring problem, well, actually, sorry, there's a typo, but Gidney and Akera, they show that you only needed like 20 million qubits in about 8 hours to factor. But so these 20 million physical qubits is this number up here, and then error correction leads to this, which is an amazing time. Actually, this is super fast to factor this number. But it also tells us that we're far away from this risk. But if you're worried about your own cryptography and public key cryptography, you should think about shifting your keys. Now, I'll just say that a lot of times people will say things like, okay, you need 1,000 qubits per logical qubit. And this comes from a simple calculation. So for the surface code, if I have n physical qubits, I get 1 logical qubit at the distance d. Logical error is suppressed exponentially in d if the physical error is below some threshold error. And when I take the log of this, you see that d basically, of course, controls the error. And for the surface code, d is only the square root of this number. And so if you say, I want to factor a number, or I need like 10 to the minus 14 error rates, it basically spits out this 1,000 number. But there are different ways to do error correction, and there's been a lot of really nice work looking at how we can basically shrink this value. For example, in this nice paper by Microsoft, they get to 50 qubits per logical qubit. The basic idea is you have to go from like local checks to distance checks. And I would say, I just advertise, we have this nice tool to look at this now. Yeah, and then I'm behind schedule, so I'll just hop to the end just to say that there's all kinds of cool things to do, but I think at the moment, the main problem is that we need to scale the hardware, and that's the fundamental challenge. And the combination between improving hardware quality, improving our quantum error correction protocols, and making the applications better will allow us to reach this advantage. And but for me, the thing which is toughest is this hardware at the moment. So with that, I'll just say I didn't talk about anything of my group, but here's my current research group. We're at the Duke Quantum Center, and I'm very happy for support we've had from the National Science Foundation, the Army, the intelligence community, Department of Energy, and I hope everyone is reminding their Congress people to support science. Thank you.
All right. Thank you, Ken. Now we will answer some questions. So if you want to submit a question, please do so in the link that Eliza has sent in the chat. So let's start off with some of the first questions. Okay, we have one from Kai Cook from the University of Utah. And they asked, to what degree and by when will quantum computing impact encryption, either of stored data, of communication, of individuals, or by the government?
So I think so it depends on what you think that scaling is looking like. But I think you probably should think about changing your things by 2030 and for sure by 2035.
Great. Now here we have a question by Howard Winston from the University of Connecticut. I've read critiques of quantum computing that say this technology isn't feasible because error correction scaling becomes prohibitive as the number of qubits increases. It would be helpful to understand why this is not the case.
Yeah, let me bring up a slide, I guess. So so again, I think the key slide is this slide. So the number of physical qubits n I need for one logical qubit depends on the error that I actually want to get to. So here, they assume that the quality of gates only gets to 10 to the minus 3. And that basically pushes this up to 1,000. I think everyone is pretty confident that we'll be able to get to 10 to the minus 4 in many platforms, which of course here just is a cut down, but it brings it down some. The more important thing has to do with this, which is the surface code, which is pictured here on the right. It's very popular from a hardware perspective because you only have these local checks. But if you had a way to have like non-local connectivity, which is represented by these far red squares here, what you see is you can actually really compactly store data. And there are many things kind of in between. So for example, yeah, Google has this idea called yoked surface codes, where you just take surface codes together and it allows you to like more compactly store information to get to the same error rate. And so I don't, yeah, I guess I disagree. I think it's true that we can't do it now, right? Because now we're like 100. But as soon as we start to getting to like this 10,000-ish physical qubit level, I think I don't see anything stopping us. And I will also say that a lot of people are like, well, quantum error correction is not going to work generically. But so far, all of the experimental evidence we've seen in the last few years, everything works like, well, sorry, I need to be a little bit careful here. So I think the thing sometimes, for example, I feel like I'm arguing with like condensed matter theorists all the time about it. Uh, the thing is, a computer is not a physical system. You basically, if you build a computer that doesn't work, you throw it away. So there's a huge post-selection on fabrication. So we've seen that when we make really good fabricated devices and we're very careful about them and we think about ways to shift software, we've been able, the community has been able in ion traps and superconductors to show this repeated quantum error correction that helps. And yeah, and then in other platforms, they've shown the basic like error correction communication. So I think it'll work. It'll be expensive for sure, but it'll work.
Great. Here's a question from Ben Tenenbaum from Sandia National Lab. They asked, Qubits are only part of the challenge. The software stack is also not trivial. Can you say anything about progress in the quantum software?
Yeah, so I think so I think the quantum software stack going from kind of a circuit diagram of how to do, your quantum information down to the actual control hardware has seen a lot of improvement. Because they're basic questions like if I'm running circuits of the same type, like I have to make sure that compilation from this kind of abstract quantum circuit idea down to like pulse level RF controls, which are happening. There's still a lot of room there, but there's not a lot of good work. The part of the software stack that I would love to see more work in on the computer science side is we don't really have tools above the circuit which help us reason about algorithms. So my analogy I always have is like object-oriented programming doesn't make your classical computer any more powerful, but it makes your ability to think about how things connect together different, which allows you to write code in a different way. Um, and I think for the quantum stack, I'd like to see more of those tools. Can we have higher level tools that help everybody reason about how a quantum computer works?
Okay, here is a question from Denmark, Elisma from the University of Richmond, who asks, can you talk about synchronization of the gates? Do you model how chaos can affect the system?
Um, so okay, so I do okay, so for almost all these quantum systems, we use RF to control them, like for superconductors, for lasers, like for lasers, or sorry, for ions. So ions, RF modulates the laser, but still these RF pulses. And what's really critical related to synchronization is the phase. So the hard thing is you're trying to keep this like complex multi-body entangled wave together, and small differences in the phases between these things, um, yeah, can really cause you grief. And that's actually what I've seen in terms of hardware, like classical hardware, watching those controllers become more available. Because when we first talked about these problems with like classical, like with hardware vendors, no one else actually has the harsh requirements on phase. Like, oh, maybe you have to keep the phase steady for like a couple pulses, but now you actually want to kind of keep the phase steady over this whole communication. Um, Now on the chaos side, uh, I think what's interesting is this randomization of this quantum algorithm that generates random circuits. You can kind of think of it as along the lines of quantum chaos, which is you make a circuit which is deep enough that the wave function gets so mixed up um, that it gets this, yeah, it has this stochastic property we're looking for, right? Now, chaos in general, um, I think the like maybe long-term answer has to do with quantum error correction. So quantum error correction allows you to effectively digitize a quantum computer. So I didn't have time to talk about it, but one of the other things that makes the resource cost of quantum error correction so high is the allowed like basic operations you do are limited by the error correction. And so if I want to do any arbitrary operation, which I want to do because it's a universal computer, I actually have to build out of a bunch of pieces. But I think by making those things discrete, just like in our regular computers where we make logical gates discrete, helps us avoid the chaos trap.
Thank you. We have a question from James Sunseri, who is also a Hertz Fellow at Princeton. And he asked, as an expert, what are your thoughts on the Majorana one chip from Microsoft? It sounds like a major jump, but it also sounds too good to be true.
Yeah, well, so I had the pleasure of being the chair of the APS March meeting this year. The talk in which Microsoft presented their results on the Majorana chip was the only session where the room overflowed this time, and we had to like bounce people out the doors. Um, and then in the end, um, my impression from everyone was uh, you basically need to measure in two bases. So in the one basis, kind of say, we'll say energy basis, Z basis, everybody was happy with the result. They're like, that looks good. And then the X basis, um, people really, there's a real spectrum, but I think the average consent was like, I don't like it's maybe there, maybe not there. Kind of needs more work to be done. So that's my sense. But I will say something a little bit more broadly, which is for most quantum computing, possible quantum computing platforms, doing single qubit operations and measurements is not too bad. And the thing which is really hard is doing two qubit operations. And so for me, like for the Majoranas, I just wait and actually, but not just Majoranas, for any platform, I wait for them to do a two qubit operation. And then the other thing, yeah, and then I will actually evaluate it. But before I see these two qubit operations, I think, okay, they're just working on building something new.
Thank you. Another question from Carol Parrish from the University of Richmond. They asked, why do you not need to worry about imperfections in the natural qubits?
Just because they're uh, I don't know, they just because the qubits are just set um by nature. So with like ytterbium ions, the level structure of ytterbium ion is just totally controlled by the Coulombic interaction, which I can't tweak, which is great because then it means every ytterbium ion will have exactly the same energy structure. The tough thing is the controls will be imperfect, right? So we still have to worry about the controls. But I do really think that the the neutral atom experiment where they showed you could just shoot a huge laser beam to do all of these two qubit gates in parallel really show like, yeah, every atom is the same, right? And we can use that to make controls easier. And
Uh,
let me just contrast it to synthetic qubits. So in the synthetic qubits, like say the superconductors, you have a Josephson junction, which is a thin layer of insulator between two superconducting metals, right? And that thin layer of insulators is just like a few atoms thick. And our ability to make that is super, like, yeah, I know it's amazing, but you cannot make them the same every time. Yeah.
Thank you. A question from David Leone, who's also a Hertz Fellow, has asked, if so far in this new administration, has your group seen any significant change in policy, funding, and or in setting the research objectives?
Yeah, I mean, um, so I mean, I think there are a few, okay, so from an academic perspective, the first change is this change in overhead rate, which sounds kind of wonky, but when you're an academic, like you don't like rent your lab, you don't pay for electricity, you don't pay for cleaning, you don't pay for people to pick up your chemical waste, you don't pay for people to check your export control, you don't pay for people to like help you with patenting your innovations that have been funded by the federal government. All of those people are paid from this overhead number. Um, Now, these overhead numbers, so at Duke University has been 60%. So in the new administration, they want to cut that to 15%. And the way that I try to think about it is that money mostly pays people. So it means 3 out of 4 people have to be paid some other way or lose their job. And that's a huge change in how universities will run. And then on top of that, at least in the administration's skinny budget, they like cut the National Science Foundation in half. They cut the NIH by a bit, and all those things. Uh, yeah, I mean, I always feel weird about it because, of course, these things all benefit. Like having these things be big benefit me. So why should you trust me that it's good to have these things that benefit me remain big? But I do think if you like the thing I tell like my family is if you go to these places where you can look at they have these tax invoices where you just punch in how much you pay in federal taxes and it splits out what things are. And you see the amount of money that you pay to the NSF will be like a sandwich, one sandwich a year to fund the National Science Foundation. And so it's also, I think, a little bit of like, um, it looks like a lot of cost cutting, which is not doing anything. So that's the main part. And then of course, yeah, I'll stop there. I could go on all day.
A question from Maxwell Riggs of Brigham Young University. You talked about problems of scaling the hardware. Is there a theoretical cap that might exist for scaling ion trapping computers?
Yeah, that's a great question. So there's not, so the way ion trap quantum computers work, I think there are kind of three scales. So the first scale is like a chain of ions. So what's nice about the chain of ions is that you can actually do any two qubit operation in that chain. And we say, all-to-all connectivity, which is nice. That chain lives on some kind of ion trap chip. Those chains can be swapped around with each other. And actually, Quantinuum's all-to-all connectivity thing is just based on swapping small chains of two ions around. Um, but then, so I think for a single chain, it's hard to think about having like more than, say, 50 ions in that chain before there's not really a fundamental limit, but there's a technical noise limit of basically heating from the trap, which is hard to think about how to make it really, really tiny. Um, on the chip, there's going to be some limit to the size of chip you can fabricate. And so then people think about a third length scale, which is how to transfer information between the different chips. People like to use photonic interconnects to make that. So basically, you entangle ion with a photon, erase the photon information that leads to entangled ions. Um, and that once you can do that, once you can actually have modules of chips connected to each other, then I don't think there's like any limit. Um, so yeah, there's no theoretical limit for sure. In practice, I think there's a limit of complexity of components, and that always, and for pretty much everything we make in the world, that leads to some kind of modular design.
Great. We have a question from Jacob Alavi from Moody Aviation. They said, thank you for your insightful presentation. I hold a bachelor's technology in computer science, and I'm currently training in missionary aviation with Moody Aviation. While my focus is now on flight dispatch and operational safety, I'm curious how concepts like quantum error correction could eventually support high reliability systems in aviation, such as secure communication, fault tolerant navigation, or even satellite coordination.
Um, so first off, if I'm trying to make a very reliable system, I would make it with classical computing. So for the most first part of that, I think the classical computing is quite good. I think one thing which is pretty interesting in quantum technologies in general is that you can use quantum sensors to build gyroscopes. And you can use those kind of quantum gyroscopes to do navigation in, say, GPS denied environments as an example. And there's actually a company called Q Control, which recently had like a demonstration with a plane comparing their quantum control thing to other methods. And that it's unclear how, sorry. It's interesting to think about how by making this quantum thing more complex with perhaps error correction, we can make those systems better and better. But yeah, so that's the thing that comes to mind when I think about aviation, because it would allow you to have a secondary system tracking your position outside of GPS and what other navigation tools you have.
All right, we have another question from Greg Tarlor, Hertz Fellow. And they asked the first question about when you thought about, oh, the first question asked about when you thought quantum computing would have an impact on encryption. I believe your answer amounted to the breaking of classical encryption would happen in the 2030 to 2035 timeframe. I believe that quantum computing is already impacting classical encryption because of the risk that a stored message may still be a valuable secret when quantum computing becomes able to reveal their contents. Well, Okay, I suppose that is not that's more of a comment than a question. I think it
Yeah,
raises
I would
an
say
interesting point.
no, I mean, I actually agree. And I want to
Hmm.
be clear that it's not, um, of course, progress could change, but the 2030 and 2035 numbers to me are not necessarily when we'll be able to break these encryptions for sure. But at this rate of progress, if our progress continues, yeah, with like, but kind of like no technological jump, just like continued technological progress around that time, yeah, you really, you really need to start getting these things in place exactly for what you were saying. That you, I mean, depending who you are, right, there could be people like holding your encrypted data already, um, waiting for that time. And I will say, like a lot of companies have already shifted to the option, at least, to have kind of quantum resilient public key crypto systems.
Hmm. Great. Another question from John Garska, who is a Hertz Fellow working with the U.S. Department of Defense. They asked if you could elaborate further on the concept of quantum entanglement.
Yeah, so quantum entanglement. Um, so I think what's funny to me is like from a math perspective, you just have like these composite systems, and the question is, can I think about the whole system as just products of these two systems? And quantum entanglement basically tells us that's not the case. And then people usually have this analogy about like my analogy is like you know, you tear like whatever you tear something in half. You tear a dollar bill in half. I send you half the dollar bill. As soon as you get your half, you know which half I have. But that's actually just classical correlation. So quantum entanglement is more subtle than that, and it actually allows to correlations that cannot be described by this like classical hidden variable model. And what it does is it allows you, yeah, from a computational perspective, it allows you to make these really interesting superposition states over over broad pieces. From a communications perspective, it allows you to have secure, uh, yeah, secure communication by having an ability to generate really secret keys, random one-time pads over a distance, which is amazing. Um, and yeah, and then I the uh, maybe sorry, this is like too much jargon, but I think it was amazing. So if you're playing a quantum game, or you're playing a game where people have entanglement, if you could solve that game, you could solve the halting problem. So it just shows that like having this entanglement stuff is pretty phenomenal. Um, and then yeah, I'm happy to talk about it more, clarify anything.
Um, Great. Another question from Kai again, who asked, what are energy requirements for quantum computing compared to conventional computers? Of course, normalized by computing power. If quantum computers use less energy, will that eventually solve the problem of immense energy needs for AI or large language models that we are seeing today?
Okay, so one thing I think is really neat about quantum computers is that the computing is all reversible except for the measurement. So in principle, you in principle, yeah, well, but in principle, in theory, you should actually be able to get to like that sort of limit. Now, the problem is quantum error correction starts to use up energy. Um, so for different platforms, for like a lot of the synthetic qubit semiconductor superconductors, they have to work inside of these dilution refriges, which cool down to 4 Kelvin, and that takes up a lot of energy. I would say for the ion trap systems, the main source of energy is lasers. But if you compare them, but I think what's amazing is if you compare them to, say, Frontier. So Frontier is like a leadership computing facility at Oak Ridge. It's an amazing computer. Um, what's neat is that Honeywell quantum computer, which runs on I mean, I would guess the amount of power you use in your house basically can do something way faster than Frontier can do. Whereas Frontier basically at capacity almost takes up a whole um, nuclear reactor's worth of energy, right? Like it's a, it is going to be lower energy, and it would be nice if we could figure out how to use it to help solve these, um, to think about ways to bring down the energy cost of AI.
Um, and let's see, we have another question from Charlie Johnson from Penn, and they asked, how about quantum computing with single photons? That's probably in reference to the question about energy requirements.
Yeah, so single photons, so what's great about single photons is they don't talk to anything. And the hard thing about turning them into quantum computers is they don't talk to anything. And so you have to figure out how to get the photons to interact in a way that you create these things. And there are companies that work on that. The challenge is you need all of the photons to be coherent. And the easiest way to do that is to somehow seed them from the same source in some sense. And I think that's probably the energy cost there.
Great. I think we are almost at the end. So Ken, is there anything you would like to say to wrap up the discussion?
Anyways, thanks for all the great questions. It's been a lovely discussion. I do think a lot of these questions, there has been research, for example, in the energy cost of quantum computing, by people in like the architecture community. Quantum entanglement is tough to get your head around, but it's interesting to see what the applications are. And there, I really do recommend some of these uh, like tutorials people have developed. And yeah, and then I hope, yeah, if you have any questions, feel free to reach out. And great, thanks for joining.